This is lesson 33 of the Quantum Mechanics, a mini lecture series titled Differential Calculus Part 1. So quantum mechanics, just like any other sub-branch of physics, has this mathematical basis, okay, which allows an accurate description of its theories. So differential calculus is one of those mathematical formalisms used to describe quantum mechanics, in addition to linear algebra, which I'll talk about later. So differential calculus is basically the study of how things change, how quantities change, okay? Like fluid flowing through a pipe, let's say. Suppose I've got a pipe, some fluid going through. Okay, it's basically how that fluid changes as it flows through the pipe system. Okay, let's say with respect to time. So I'm going to try and do the best I can to introduce differential calculus for those who aren't really familiar with it, particularly those who are in junior high school. So let me first provide you with a simple example which illustrates how differential calculus works. So suppose I give you a car and I'll take out its speedometer. Okay, the speedometer is the thing on the dash which tells you how fast the car's going. Suppose I take it out and I only provide you with gauges, okay, with instruments containing a distance meter, okay, D for distance, and a timer, T, okay, on your dashboard to tell you how much distance you've covered and in what amount of time. So let's say you drive for a distance of X meters, okay, in Y seconds. I'll then ask you to tell me what the acceleration of the car is. So how would you do this? Answer is differential calculus, okay? A for acceleration. So mathematically, you can express your position at a certain time along your journey as follows. X, T. Okay, X is your position, and T is the time it takes for you to cover that position X, okay? X in a certain amount of time, T. So how would you then calculate your velocity, okay, i.e. your speed in a certain direction? Well, speed is just your change in position with respect to time, right? So mathematically, here's how we would write it. Vt is equal to dx over dt, okay? Speed is change in position over time. Okay, change in position over time. That's what the D's stand for. So it might look a bit complicated, this expression at first, but in actual fact, it's just exactly what I mentioned here in words. Speed, V of t, is just the change in position over time. Okay, to then work out your acceleration, you would need to determine the difference between your final speed and initial speed. So A for acceleration, okay, in a certain amount of time. Okay, it's given by dv over dt, which is just your change in velocity. You can also use the symbol delta v over delta t. Okay, the d and the delta can be used synonymously, okay, simultaneously. The d and the delta, I should say, they're synonymous, okay? They're pretty much the same thing. Okay, acceleration is how fast you're going in a certain amount of time. Okay, delta means change in. Okay, it's the Greek symbol delta, means change in, okay? So delta V means your final velocity minus your initial velocity. Similarly with time, your final time minus your initial time, okay? So delta T as well, let's say delta T, the change in temperature, that's the final temperature minus the initial temperature. Okay, let's suppose you wanted to work out delta T over, let's say, 5 hours. So the acceleration, A of t, is the change in velocity with respect to time, which is just your final velocity, the difference between your final and initial velocities, divided by the difference between the final and initial times. Okay, and this idea of rate of change, given by d over d, let's say d over dt in this case, change of velocity with respect to time, this is actually called the derivative. It's got another name called the derivative. I'll talk more about this in a subsequent video. And in maths, when you're finding the rate of change of a certain quantity, what you're actually doing is finding the quantity's derivative. Okay, in a nutshell, differential calculus requires us to find how a quantity, like position, varies over time, for example.